Is that running? It is. Good. Okay, so reflection. And you can see a few things going on here, but one of the reasons we have rainbows is because of both reflection and refraction. And there's that white light going into just a water droplet in the air, and there's reflection occurring here, but there's refraction occurring here and here as well, and that results in the white light being split into these 7 colours. What are the 7 colours? Yep.
Red, yellow, orange, green.
Oh God, you're confusing me. Red, orange, yellow.
Green,
blue, indigo, violet.
Blue, indigo, violet. Yes. Roig Biv. So please remember that. It will come up. Now, key learning intentions, we talked about that. We're looking at the reflective properties of light. We've already talked about photons and light speed a little bit. Now we're looking at luminous versus non-luminous, light-giving versus non-light-giving, transparent, translucent and opaque. Those 3 terms are key. The law of reflection is key. Angle of incidence, angle of reflection, virtual image, concave mirrors, convex mirrors, and total internal reflection. And you'd probably go, reflection is a bit abstract, this total internal reflection bit, and how is this real to me in a meaningful way? The simple fact of the matter is, a high-speed fibre optic cable uses total internal reflection. So the world runs on it. Okay, and I was reading in the newspaper yesterday that the Liberal Party's quite bad NBN, which is currently valued at $51 billion, and is so bad at doing what it does that it's going to be devalued. And the actual Labor government's plan, which would have had fibre optic going to individual houses, is ultimately would have been cheaper and would have worked. So $51 billion of your parents' and guardians' money has just been blasted into the ether. So for $51 billion, you could actually make 100 clean power plants and completely revolutionise power in Australia. Yes? Oh, 40 billion for submarines that are not going to be used either.
What's the economy of Australia?
Oh, the GDP?
Yeah.
I'm a bit blind in that respect, I apologise. Dylan, I hope you don't have a phone, because that would be bad. Or a smartwatch, equally bad. Okay. Now, this slide here, yes, it's a lot. This slide here you've seen before, and it's just a bit of a review. Okay? So, these are light waves. There's our little Roig Biv down there. We talked about low energy. Low frequency is low energy. High frequency is high energy. We mentioned that all of these move at light speed. Radio waves, microwaves, everything like that moves at light speed. They're all photonic. They move through a vacuum. Now, luminous objects emit light. The sun, for example, or light globes. Okay? The moon is not luminous. It reflects light. Okay? So, non-luminous objects don't make their own light. They can be seen if they reflect light. So anything that reflects light can be seen. If something absorbs light, or most of the light, it's black. If it absorbs all of the light, it would actually appear almost like a black hole. So if you had a poster of something that had, perfect absorption properties, it would really, you couldn't get any contrast on it, and you'd see it as being just almost a hole in the wall. Now, you see an object because light has bounced off it, entered your eyes. An image of what you're looking at has formed on your retina. So there's the red apple, white light coming in, but only the red light reflecting and reaching your eye. Okay? And so that's fundamentally what we're seeing. Although light travels in a series of straight lines to get to your eyes, it changes direction whenever it reflects or refracts. Okay? So in this case, everything except red is being absorbed. The red is reflecting though off that surface. So the nature of the apple skin is such that light of the red wavelength will actually, of that frequency, will not be absorbed. It will be reflected, and it bounces off and reaches your eyes. Okay, now, that's almost not very bright. Probably turn those off, I reckon. That's not bad. Okay, now you'll need to know these terms. Transparent is see-through. Light passes through and it doesn't lose energy when it does that. So it just moves through, and that's why you can look through a glass window and you can see clearly what's happening outside, because the light that's bouncing off everything, the light that's bouncing, again, the light that's bouncing off everything reaches your eyes, and it's not slowed down, it's not bent. And that's actually really important as well. Okay. Now, a translucent substance is something that is only partly see-through. So rays of light can go through, but they scatter. And so you've seen these in doctors' offices, or you've seen them in doctors, dentists' offices. They're the windows that have that white film usually on them. And you can see people moving around back there, but you can't see clearly what's going on. Opaque is not see-through. Light bounces off, or it is absorbed. And so there you go, transparent, you can see the checkerboard pattern, translucent, it's blurred out, and opaque, you can't see. Yes, Dave?
So is that how one-way glass works?
You mean one-way glass, that actually is more of lighting than anything else. They have a bit of a film on it, but it's dark in the room behind you. And it's bright in this room. So of course, I think you've probably seen them at home when it's you're in the house and it's dark outside and the lights are on, and you can see a reflection of yourself in the glass. You can't actually see out of the house, and the same sort of thing is happening there. Now, reflection changes the direction of light, and this is really important. The angle a light ray makes is the same before and after the reflection. So the image is right way up, but it's flipped. So if I look at myself in the mirror, I'm still upright, but this ear, which is on my left, appears on this side in the mirror, which if that mirror person turned around would be on the right. So the image is flipped, but still right way up. And these angles are measured from an imaginary line called the normal, that line there, and that is 90 degrees perpendicular to the mirror. So basically, if you've ever played pool or billiards or something like that, or hit a ball off a wall, or even down ball on the courts, the angle that it comes in is matched with the angle as it leaves. So the angle of incidence coming in, if that was 30 degrees coming in, will bounce out at 30 degrees. And that's true for all the light waves coming in, and that's why you get an even reflection if you've got this flat reflective surface, plane mirror. And that's the law of reflection. The angle of incidence equals the angle of reflection. Now, when you draw these types of mirrors, you need to have arrowheads going in and out, or at least one arrowhead somewhere making directionality clear. Labelled angle of incidence, that one there. Labelled angle of reflection, that one there. And on curved mirrors, arrowheads indicating parallel lines coming in. We'll see that when we do curved mirrors. But that's the rule. You will need to be able to draw these. Okay, so you get something like that. Now, that's a plane mirror. Okay, and the image is clear and understood. It appears behind the mirror at the same distance. So that's no surprise to you. When you're standing a metre from a mirror, your image looks like it's standing a metre from the mirror on its side of that surface. Okay, and it's called a virtual image. Okay, it's reversed but right side up, and the size is the same as the object. This is what a virtual image means, and this is very difficult for students. This idea of virtual images versus real images. Okay, virtual images. A virtual image, you can't touch it. Okay, that's the short version. Okay, you can see the mirror you, but you can't touch that image. But that projector is putting an image on here, and I can touch that image. Okay, there's a lens in there, and it's the same with mirrors as well. So a real image is considered to be one that you can touch, and we're going to have a little bit of a play with that when we do lenses. I'll get the magnifying glasses out again. You'll hold them up to the board, about that far from the whiteboard, and you'll get a picture of the trees outside. So the light coming through the window will go through the lens and it'll go onto the board, and you can touch that. And that's considered a real image. The virtual images are formed in the virtual world. You cannot touch the image, but it still exists. Virtual images cannot be captured on a screen or directly onto film. So the classic camera, or even your eye, works the same way. When light goes in through that lens, it focuses it onto a film that is exposed, and then you can actually develop that film, and you have a picture. But these are virtual images. They can't be captured in that way, because, so it's slightly different. Now, mirrors. These are differently shaped mirrors. So a concave mirror, and you've seen these before, parallel light rays reflect in towards a focal point. Okay, so what happens is these lights come in all at the same angle, but this one here is reflected down here, this one here, here, and it all comes to a focal point. And so, obviously, if this was, well, actually no, let's see. Now, where the object, these ones are hard to remember. We'll go through it, we'll look at some examples, and then we'll go through it again next class. Where the object is inside the focal length, the image is clear but distorted. That's inside the focal length. Reversed and right side up, and magnified. So, if that's the focal length, if you were standing here, you would have, have these properties. Reversed, right side up, magnified. So you'd have a big head, okay, like a funhouse mirror. If you're at the focal point, standing there, you can't see your reflection. You're just not there. And when an object is outside the focal length, the image is clear but distorted, reversed and upside down, and not magnified, so it can be the same size or smaller. Now on this slide here, that's what I'm talking about. See how the girl is inside the focal point and her reflection is really large, okay? And her brother is outside the focal point and he is either the right size or smaller than he would be normally, okay? They're the hardest mirrors to remember what's going on. Yes?
He's also upside down.
Is he upside down? I can't
Yeah.
actually... Oh yes, sorry. I forgot to mention it. Yeah, just here. Reversed and upside down, yes. So I couldn't see from my angle. There he is, right there. Upside down. He's outside the focal point. So if you look inside, on the inside of a spoon, if you can get inside the focal point, you'll be magnified. So you can do that with your fingertip. If you're outside the focal point, you're upside down. So remember, when the spoon is like this, you're upside down. Okay. Now, this is a convex mirror. They're harder to visualise what's going on. You've seen these on car mirrors or caravan mirrors, yes? Where you put that, it allows you to see a little bit more, but you'll notice, look at the cars here, the size of these things. Look at the cars, how they appear here, okay? So that's why with these particular mirrors, if they are on a vehicle, they'll always have that sticker. Objects are actually closer than they appear, because everything looks small, okay? Now, a convex mirror, the rays of light reflect outwards and travel away from the focal point. So, of course, because of this angle, this is bouncing away from the focal point, so you have to draw these dotted lines in to calculate where the focal length of this particular mirror. Now, produces an image which is reversed and right side up, which is useful for mirrors if you're driving. You don't want to have an image that's upside down and larger. That would be of no use. Yes?
Wait, if that was taking a photo of, then where's the camera?
Oh, it's going to be just to one side.
Oh.
You know, I mean, like, have you ever seen this car mirror with these on there, and you just look out and it bounces? Yeah.
Yeah.
Okay. Now, reverse but right side up appears to be behind the mirror, so it's a virtual image, but farther away and smaller than the object. The closer the object is to the mirror, the larger it gets. So that's why these mirrors, they have their uses. You might even see that there's a couple of streets in Bendigo where they'll have these mirrors. Because of the odd angle of the streets, they'll put these mirrors up there so you can sort of see around the next corner to make sure, like you can't see very well, but you can certainly see movement, like another car approaching, and that gives you a warning. Yes?
We need like mirror glasses so we can see behind us.
No, you don't.
Or
Or a little
in
camera.
front of us either.
Now, this is my summary, and this is lenses and mirrors summarised on one thing. But in terms of the mirrors we've looked at, we have flat mirror, virtual image. So like a spoon. Object inside the focal length is reversed, right side up and magnified. So you can see concave mirror has the 2. Object outside the focal length, reversed upside down, not magnified. A convex mirror is reversed, right way up, smaller. And there are lenses, and we have even the eye over here as well in terms of lenses. So that's what's covered in this slideshow. These all produce virtual images. The real images are only convex lens and eye. Yes?
Is that why... Oh, I forgot.
Oh, okay, I took too long.
Oh wait, no. Is that why when you look the wrong way through a telescope, everything looks farther away? With the
No, that's
convex
2
mirror?
lenses, at least 2 lenses going on in there. So, or there might be a mirror in that particular telescope if it's a reflective Newtonian telescope. Okay, so there you go. That will be a useful cram card for you. Now, part of the curriculum is finding practical uses for these sorts of things. So we'll cover a little bit on this. This is total internal reflection. And maybe, actually, you're doing the swimming sports this week, so if you're in the pool, lie on the bottom of the pool, not for too long, and again, freak everyone out. Okay. And if you look through the water, you can see people standing above you. But if you look further down the pool, at one point, it's going to become like a mirror. You won't be able to see out of the water anymore. Yeah, looking straight up, I can see out of the water. But you get on a certain angle, and the light will actually, it'll be from the bottom of the pool, will be hitting up and bouncing and reaching your eye. The light from outside won't be reaching your eye anymore. So it's a bit weird. This is total internal reflection, and you can see that there. The light can't escape from the substance it's in. The phenomenon is known as total internal reflection. Oh, Mr. MASC, how is this useful? That's, if you're cutting diamonds, that's what you're going for. You want that light bouncing around as much as possible so you get that sparkle, you get that fire. Okay? Not a simple thing to do. There's another example of total internal reflection. So there's a light source here, and we'll look at the light when it's leaving the glass and going into the air is bending. That's what happens. That's refraction, and we study that next. But you can see here the angles are slightly different, but you get to a severe enough angle at this end, and it will actually bounce on down. Okay, and so the light won't escape. And it's the same. So give that a go when you're at the pool if you're doing something. That's an example of fibre optic cables where they use total internal reflection. Just boom, 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 boom. So they use light to transmit data. And they've been playing around with that for about 30 years. And they originally sort of came up with these things to show that yes, you can send light down a cable, but now of course they can send it a lot of information down fairly small cables, and that is the basis of the internet as we know it today. Okay, so very, very important in that respect. Endoscopes also very, very important. They use the same principle, total internal reflection, and used by doctors. So he's not only looking through that, but he's got tools as well that he can manipulate. So my wife had some surgery last year, and all she has is a scar here, but they did major surgery, and they just looped it up, and she had surgery on her right lung, and so they had to deflate it. They're pumping extra oxygen into the left lung, and then they start working, and so I don't know, it seems extraordinary to me, because of course, yes, they're looking through that. They've got a little light source so they can see, but effectively they're having to manipulate tools in this incredibly confined environment and perform surgeries. And then, of course, you only have like a few stitches out here. And in some cases, you go home within a couple of days. Whereas in the old days, to reach that lung, open it up, work, and then have to close everything up. And they're going to be in hospital for a long time. So, endoscopes, yeah, are incredibly important for keyhole surgery. And that's the last little bit. So this was in 2012, where they were looking at invisibility cloaks or invisibility things. This thing here is actually invisible to one of the wavelengths, radio or X-rays perhaps, but not to visible light. This is just cheating. They just have a white coat on and they're using a projector like that. And so they have a camera behind the person filming, projecting the image onto the person from the same distance. And you get this vague see-through type thing going on. But it's not the same. The idea is though, ultimately they will get this. If you can get light to go around an object, not be absorbed, to just get around the object and go out the other side, it would be invisible to you. You could touch it, it would be there, but it would just not be visible. Yes?
There's this video that I saw about they did a small scale version, which was still really expensive,
Yes?
and that you can put like your finger